Hello all, and welcome to our first video in our series dealing with electrochemistry. That is the topic we're going to be learning about, the last topic we are going to cover this year. Apologize for that writing, I gotta get used to this, but electrochemistry, you can fill in the rest. We're going to take this section by section. First one, very, very important now. Section 21.1. Now, before I get started with the first section, real quick, the very first couple paragraphs of this section actually do a quick review. It's what's literally labeled as quick review of oxidation. Electrochemistry deals specifically with redox chem, oxidation and reduction, something we did cover all the way back in chapter 4. Okay, so this section is a quick review, and more importantly now, balancing. So the quick review. You can read the first section in the first just couple paragraphs does a quick review of this, but I would highly recommend going back all the way to chapter 4 and really focusing on the things we discussed all the way back then. Things like, what does it mean to be oxidized? What does it mean to be reduced? Remember, oxidation is losing electrons, reduction is gaining them. Remember the acronym OIL rig. Oxidation is losing, reduction is gaining. That we covered all the way back at the beginning of the year. Highly recommend going and reviewing that. Other important thing to review are your oxidation numbers. Being able to look at a chemical formula and know what each individual element's oxidation number is. Those rules are also located in chapter 4. You can also do a simple Google search and review that information as well. But something you definitely want to cover and review before diving into this chapter are those ideas we covered on redox all the way back in chapter 4. Okay, now the new stuff that starts off this in this chapter is all about balancing redox reactions. Now, balancing, I know you're probably thinking, well, I know how to balance a reaction. Well, of course you do. Well, you don't know some of these. They do get kind of rough, so buckle up. We'll start with the simpler ones, the more common ones. This is a process known as balancing half reactions. Half reactions. This whole idea is you take a redox reaction and you split it up into the reduction and the oxidation. We're going to start by just kind of looking at a quick example here. These usually don't take a lot of time, and some of you might be able to do this pretty quick, but I'll show you it step by step the first time here. If we take a reaction, chromium plus cadmium ions, that's CD2 positive, goes to cadmium solid, and chromium ions, chromium 3 positive. Now, we would be expected to balance this reaction. Now, I know you might be thinking, if you look at it, you might notice that we have one chromium here and one chromium here, and one cadmium here and one cadmium there. It looks balanced. One atom of chromium is one atom of chromium, that's balanced, and cadmium is cadmium, those are balanced as well. But the problem with redox reaction is they have to be balanced not only for atoms, but they have to be balanced for charge. The charge on one side of the reaction has to equal the total charge on the other. And if you'll notice, this has no charge, plus a positive 2, that's a total of positive 2 on the left, and that does not equal the charge over here. This is 0, but this is a positive 3. So a positive 2 charge does not equal a positive 3, and we have to balance that out. And again, some of you might be able to do this pretty quick without going through all these steps, but sometimes these reactions can seem a little complicated, so I'll show you the steps. What we want to do is we want to divide this up into the oxidation and reduction half reactions. So if you'll notice, chromium goes from Cr to Cr3 positive. Okay, so chromium is losing electrons in that process. It's going from the no charge over here, no charge, to a charge of positive 3. So it lost 3 electrons in that process. So I'm going to write that half reaction. I'm going to write here Cr goes to Cr3 positive, and 3 electrons came off. Okay, I'm going to label this over here as the oxidation. And we also should want to be able to identify what the reduction is. So that has to be, first of all, our other substance. Cadmium here is a positive 2, and it became cadmium solid. So it gained 2 electrons. Oh, fudge. So I'm going to write that half reaction here. Cd 2 positive plus 2 electrons gives me my Cd with no charge. So this is the reduction. Now I've split it up into each half reaction. Now we want to be able to combine these back together to get a balanced overall reaction. In order to do that, we have to make sure that our atoms are balanced, and as we already pointed out, they already are. 1 Cr to 1 Cr, 1 Cd to 1 Cd. But the problem is the electrons are not balanced in each reaction. Here, chromium lost 3, but down here, cadmium only gained 2, and that can't happen. So what we need to do is we need to multiply each of these reactions by a factor so that our number of electrons are the same on opposite sides. So we have 3 and 2 electrons, so we need to multiply our oxidation reaction by a 2 and our reduction reaction by a 3. If I do that, see here, if I do that, I'm going to multiply oxidation by 2, so I get 2 chromiums, and this becomes a 6. And my reduction gets multiplied by 3, so I get 3 cadmiums, 6 electrons, and 3 cadmiums. So now the only thing that mattered was that I make sure my number of electrons are the same. And since they are on opposite sides of the arrow, these 6 electrons are on the right, these 6 electrons are on the left. When I combine these two half reactions, these electrons cancel out, which is exactly what's supposed to happen. So if I combine to get my overall balanced equation, I write whatever's on the left, 2 chromiums plus 3 cadmium ions, turn into 2 chromium ions and 3 cadmiums. And there's our overall balanced reaction. We see that atoms are still balanced, 2 chromium, 3 cadmium, 3 cadmium. And charge is now balanced as well. This is neutral, so who cares? 3 times a positive 2, that's like a positive 6. Over here, 2 times 3, charge, that's like a positive 6 as well, and neutral, so that's like nothing. So the charges are balanced on both sides as well, and this would be a balanced redox reaction. So like I said, some of you could probably do this math real easily without dividing everything up into its half reaction. It is a good skill to be able to take this overall redox reaction and split it up into the 2 half reactions. So definitely be able to do that. But in terms of just balancing, if you could look at this and just simply say, okay, I know it's a positive 2, positive 3, so I need 3 cadmiums, 2 chromiums, and you could do the math from there. Fantastic. The faster the better. You don't have to go through and show all this work if you don't have to. Okay, now something you will want to show a lot of work for and show the steps for is what happens if we have to balance a redox reaction in an acidic solution. This takes it up a notch. So let's check this out. Okay, so now let's balance redox in an acidic solution. this gets real fun real quick. So this one I am going to break down and number step by step because I think it helps, and there are quite a few steps here. So first of all, we're going to start with our unbalanced chemical reaction. We have Fe, 2 positive, plus our dichromate ion goes to Fe3 positive and a chromium ion. So here's our unbalanced reaction. Now this looks really off. It might be very unsettling because if you think about it, here's an oxygen, and the oxygen's disappeared. They're gone. That's impossible. That breaks all sorts of laws. So we need to balance this, and those O's have to be accounted for. We're told that it isn't an acidic solution, so we need to go step by step. Step number 2 here, we need to split up our half reactions. So separate into, that's supposed to be an E. You get the idea. Separate into half reactions, R, X, and S. Okay. Let's see. We're going to separate. I'm going to make my oxidations blue. Our oxidation here, if we look at the top, let's take a look at iron. That's the easiest. Fe2 positive to Fe3 positive. In order to do that, iron needs to lose an electron. So that right there is our oxidation. So I'm going to write our oxidation Fe2 positive goes to Fe3 positive. And I'll stop right there. I know some of you might want to be adding in that electron, but we're going to hold off on that for right now. Again, I'm going to go in ordered steps. Next up, we need to identify our reduction. So that should be our other 2 chemicals here. That's our dichromate, Cr2, O7 to negative, goes to Cr3 positive. And those of you that are more familiar with our oxidation numbers, if you are keeping track, oxygen's oxidation number is typically -2 times 7, that's like a -14. If I need a -2 left over, then this has to be a total of +12, and since there's 2 chromiums, each chromium has a +6. +6 went to +3, that means chromium must have gained electrons. That's how we would know this is our reduction. Again, if that seemed pretty quick to you guys, then definitely go back and review your oxidation numbers back from Chapter 4. Okay, now let's go on to our next step. Once we've split it up into our oxidation reduction half reactions, here's what we do. Step number 3, balance every atom except O and H. So you ignore oxygens and you ignore hydrogens, but you balance everything else. So if we take a look at our 2 half reactions, iron, here in our oxidation, 1 iron goes to 1 iron. This is balanced, 1 atom and 1 atom. That's good. I don't need to do anything there. I come down here, I'm ignoring oxygens, and I'm just going to focus on any other atom, any other element other than that, and that would be my chromium. Here I have 2 chromiums, and here I only have 1. So this needs to be balanced. So I'm going to show that here. We're going to balance our reduction. Oh boy, that's not what I wanted. Okay, here we go. Oh, I wanted red. Sugar. Okay, good. That's gone. Here we go. Chromium 2, O7, 2 minus, goes to 2 chromium 3 positives. Simple as that. All I had to do was balance elements other than O and H. So 2 chromiums goes to 2 chromiums. So my my reduction half reaction is balanced, other than O and H. And again, our oxidation's already good. Alrighty, let's keep it rolling. Ooh, I think I'm still recording. So our next step here, I believe we are on step 4. So here we go. Oh, that's not the letter I wanted. For reactions in acid, here's what we do. We add water to balance O atoms, and H plus to balance hydrogen atoms. So this is where things get interesting. If you guys recall, take a look back. If you look at our oxidation with our iron, there are no O's or H's in the oxidation. So that half reaction is totally fine. We don't need to add water to it, and we don't need to add H+. There's no reason to. There are no O atoms and no H atoms. But our reduction has O atoms. So we need to balance that out. So here's our reduction. Cr2O7, 2 minus, goes to 2Cr3 positive. That's what we have so far. I have 7 oxygen atoms here. So I need to add enough water so I have 7 oxygen atoms on this side. So I need to add 7 water molecules, 7 H2Os. Right now, that takes care of my O's. 7 O's and 7 O's. Again, chromiums are still good. So far so good. We've created another problem though. Now we have hydrogens that came out of nowhere. We have no hydrogens here, but now all of a sudden we have now 14 hydrogens on this side. So in order to correct that, I need to, as the direction says, add H plus to balance out H atoms. So I'm going to add 14 H positive atoms to the left side. And that gets added to our dichromate. And that gets us our 2Cr3 positive and 7 waters. Okay. Now we have a half reaction, right? This is just half the reaction, where all of our atoms are balanced. 14 H's, 14 H's, 2 Cr's, 2 Cr's, 7 O's, 7 O's. So we're good. That step is now taken care of. Moving on to step number 5. Here's where we start taking care of charges. To take care of charges, add electrons to one side of each half reaction to balance charges. So now if we go back to our iron oxidation, Fe2 positive goes to Fe3 positive. Here is where I would add my one single electron. That takes care of my charges, because positive 2 is equal to 3 positive plus 1 negative. A little bit of simple math there, but you have to make sure that your charges on both sides are equal. Let's do the same thing to our reduction. If we take a look up at our reduction here, we've got here on the left side, follow me along now, we've got a H positive, but we have 14 of them. So that's like 14 positive. Plus one single thing that's a negative 2. So 14 positive plus a negative 2 gives us a positive 12 on this side. Let's see if it equals this side. 7 waters, that's neutral, so that's nothing. 2 3 positive charges, so that's like positive 6. So we have a positive 6 here and a positive 12 here. Obviously they do not equal. So I need to add electrons. Well, since I'm adding negative charges, I need to add them to this side. And I need to add 6 of them, because positive 12 plus negative 6 equals positive 6. So that's what we're going to do down here. We're going to have 6 electrons plus our 14 H positives plus our dichromates goes to 2 chromiums plus our 7 waters. So as of right now, we have 2 half reactions balanced for atom and charges. So now, starting to wrap up. Let's move on to step 6. Okay, step number 6. Here is where we make sure, oh boy, that is supposed to be the word sure. We make sure electrons are equal in both half reactions. That's, oh boy, that's supposed to say reactions. Reactions, there we go. If we take a look at our 2 half reactions there, we see that the number of electrons are not the same in both. Our oxidation is actually significantly lacking. So if you take a look, we have 1 electron in our oxidation, but 6 electrons in our reduction. So we need to multiply our oxidation by 6. So if we multiply the whole thing by 6, we wind up with 6 iron. Whoops, that's supposed to be iron 2 positive. We have 6 iron, 2 positives. It goes to 6 iron, 3 positives. And 6 electrons. And that matches up nicely with our reduction, which I'm going to rewrite here. 6 electrons plus our 14 H pluses plus our dichromate goes to 2 chromium ions plus our 7 waters. Okay, and we're almost done. At this point, we can combine half reactions. Combine them both, making sure to cancel out anything that needs to be canceled out. So we see in our above work, our 6 electrons cancels out our 6 electrons, right? They're on opposite sides of the arrow, so they cancel, and that's it. Nothing else does cancel. And we wind up with our overall balanced chemical reaction, 14 H positives plus our dichromate plus 6 irons, 6 iron ions, goes to 6 Fe3 positives plus our 2 chromiums plus our 7 waters. Run out of space there. So there's our nice, neat, fully balanced chemical reaction in an acidic solution. At this point, I suppose you can almost add an 8th step. It's not really that necessary. You can check, right? As with everything balanced, you should be able to check to make sure that charge is the same on both sides and atoms are all the same on both sides. So if we look at our atoms, 14 H's, 14 H's, 2 CRs, 2 CRs, 7 O's, 7 O's, 6 FEs, 6 FEs. If you look at the total charge, again, some simple math, 14 positives here, plus a negative 2, that gives us positive 12, plus another positive 12, 6 times positive 2, it's positive 12. So now we're at positive 24 on the left side. Over here, this is a positive 18 plus another positive 6, that's positive 24, plus a neutral molecule. So that's positive 24 on this side too. So we are all good. And there we have a balanced chemical reaction in an acidic solution. Fantastic. Okay, now I know what some of you must be thinking. Wow, it's a lot of steps. Yes, it is. Do not skip any of them. It takes very careful counting, just as with balancing anything. A miscalculation or a miscount of any one atom or charge can result in a nightmare of a reaction trying to balance, and it will never work out. So please make sure you're careful with adding up your atoms and counting your charges. The other thing is, some of you might be asking, well, what about a basic solution? Well, I am so glad you asked that, because yes, we do need to know how to balance in a basic solution as well. Good news, it's not that much different. In fact, I'll go ahead and summarize that right now. You follow all the exact same steps. Okay? If a problem tells you you need to balance a reaction in a basic solution, we're going to say here, follow same steps. Same steps as in an acidic solution. The only new part to this is right here. After step number, let's see, what is it? We called it after step number 4. Okay? If you look back, I'll kind of take a break right here. If you look back at step number 4 told us for an acidic solution you add water to balance O's and H pluses to balance H. It makes sense. H positives, right? That's your acid, your acidic solution. You do the exact same thing in a basic solution. You treat it like it's in an acidic solution. So you do step number 4. But then immediately after step number 4, okay, this is the important part. Immediately after step 4, add OH minus to both sides of the reaction for every H positive. Okay. So in our previous example, if you take a look back, after step number 4, we had 14 H positives on the reactant side to our reduction. So if this was in a basic solution, right after you've done that step, you would add 14 hydroxides to both sides of the reaction. You would add 14 OH minuses to the left and 14 OH minuses to the right. You do that to cancel out the H positives. Okay? And then you're left with OH minuses hanging around on the right side. That's how we do it. So everything else is exactly the same. You pick up right where you left off, but there's this little added step called a 4.5 step. 4.5 step, that you add OH minuses to both sides. I'm not going to go through an exact example of that right now here. If you guys want, you can take a look. If you've been following along in the textbook, you can take a look on page 922. On page 922 goes through a great example of how to balance in a basic solution. Gives you a step-by-step breakdown example of that. You can also take a look in course sites. If you log into course sites, click on chapters, go down to electrochem, and I have written out instructions for how to balance in a basic solution. I used to have my students, all of them, read those steps on their own. So if you take a look there, all the steps are outlined, as well as an example that I go through. I've got a sample problem up there with an answer that goes right along with it. You guys are going to be getting sample problems, your homework here, practice problems in a little bit, so you have plenty of opportunity for practice there. Answers are all up online on course sites for those as well. So take a look to see how you're balancing everything, and make sure you can follow those steps. And then you can balance just a general redox reaction, and then you can also balance in an acidic solution, and you can balance in a basic solution. It's really just following steps. And the best way to make sure you guys know those steps is to practice and go through it as many times as possible. So that's what the rest of this time here is going to be spent doing. You're going to get a sheet here with, if I'm not mistaken, about 6 reactions to balance in an acidic solution and 6 reactions to balance in a basic solution. Try those out. Take a look at the answers on course sites. Make sure you're getting a majority, if not all of those, to work out. If you follow the steps, I promise they will. Okay, till next time, we'll start looking at our galvanic and voltaic cells. Cannot wait.